In 10 trillion years, almost every star will be gone. The sky will be near black, lit only by faint embers. You can picture the cosmos becoming cold, dark, and lonely. Night skies in that era will show hardly any tiny points. This time marks the end of the stelliferous era. That era is when stars form and shine continuously. It matters because stars make heavy elements and light. Star fuel runs out and new star formation slows. Massive stars explode quickly, while small stars burn slowly. Red dwarfs can burn for about 10 to the power of 13 years. By contrast, giant stars die in mere millions of years. Over trillions of years, star formation cannot keep up. Gas gets locked into remnants and galaxies dim. So the picture is clear, bright starlight fades away. Long after stars die, remnants drift through empty space. A white dwarf is the core left by a sun-like star. These remnants matter because they contain most leftover baryonic mass. White dwarfs cool, they radiate mostly in infrared for eons. Neutron stars remain compact and sometimes produce magnetic bursts. Black holes trap light and merge to release gravitational waves. Slow accretion and rare collisions keep sparse activity ongoing. For scale, a white dwarf packs solar mass into Earth-sized volume. Many galaxies could host billions of cold white dwarfs eventually. Net result, remnants dominate the mass and faintly glow. There is another slow possibility: protons might decay. Proton decay is a hypothetical process breaking protons into lighter particles. This matters because proton stability keeps atoms and chemistry intact. If protons decay, atoms would slowly disintegrate and chemistry would end. Grand unified theories predict decay via positron and neutrino production. Experiments only set lower bounds on proton lifetimes so far. Current limits suggest lifetimes exceed 10 to the power of 34 years. If lifetimes are near 10 to the power of 35, matter decays sooner. So the fate of atoms depends on particle physics beyond our tests. Black holes evaporate very slowly via quantum Hawking radiation. Hawking radiation is quantum particle emission at an event horizon. This matters because black holes might be the last hot objects. Quantum fluctuations create particle pairs near the horizon and separate them. Lighter black holes radiate faster, losing mass as they emit. Supermassive black holes take astronomically longer, but still evaporate eventually. For example, a million solar mass black hole takes unimaginably long to evaporate. Estimates put that near 10 to the power of 80 years. Net result, by 10 to the power of 100 years, few remain. After all evaporation, the cosmos becomes a sea of low-energy radiation. Imagine vast wavelengths and photons stretched across enormous space. This matters because usable energy becomes almost non-existent for engines. Particles drift apart and interactions become vanishingly rare over time. Residual photons have wavelengths longer than galaxies, carrying negligible energy. Bound clusters slowly unbind as heat leaks and orbits decay. So the long-term universe is cold, dilute, and very quiet. Even then, rare flashes still puncture the vast darkness. These events are tiny collisions or captures in sparse regions. They matter because they concentrate energy briefly for possible observers. Two white dwarfs might slowly spiral together and then merge. A single merger can release heat, light, and gravitational waves briefly. Simulations suggest some collisions occur even after 10 to the power of 15 years. So sparse fireworks remain against an otherwise silent backdrop. Could intelligence survive in a trillion-year cold universe by cunning? Survival boils down to energy management and information preservation. Civilizations might slow metabolism drastically and ration scarce power carefully. They could harvest Hawking radiation or tap rare merger events. Mechanically, this means building colossal collectors and running ultra-low power computation. For scale, spreading computation over 10 to the power of 12 years saves energy. Even so, entropy steadily erodes structure, making indefinite survival challenging. So the picture is nuanced. Survival is possible but costly. Now consider the very farthest future after black holes evaporate. If protons decay, atoms vanish and chemistry ends completely. This endpoint matters because it removes the substrate for memory and life. Particle counts fall and only leptons and photons remain abundant. If protons survive, degenerate remnants persist far longer than chemistry. Either way, the cosmos becomes simpler and memories fade into noise. Bottom line, ultimate fate hinges on particle physics beyond current reach. Remember, the universe becomes cold, dark, and dominated by remnants. If this fascinated you, subscribe for more calm, big-picture science.